basis, we first want to give a definition, and the definition is as follows. So let V be a vector space. So V is a vector space, then the subset V of the vector space V, which is equal to which constitutes of the vector V1, V2, and Vn, is said to be a basis. Is said to be a basis of V, of the vector space V, if V itself is linearly independent set of vectors. Okay. So to have a basis for a specific vector space, we should have a linearly independent set of vectors, which means that the number of vectors should be the minimum possible. Okay, we should not have redundant vectors or extra vectors. And the second condition for B, when B is a subset of vector space V, to be a basis of this set, we can say that B spans V, which at this span, this means that we can describe any point in V using the vectors which compose the set itself. And we can write this one. This also means that the vector space V is equal to the linear combination. So this is how we denote it, okay? With this, we mean that the vector space is spanned by the basis B. Now, we have also a couple of, so we have a theorem which we can put it forward. And this theorem states that for any matrix A, which is a square matrix, and this is how we denote the square matrix, we say A is n by n, then the following statements are equivalent. Following statements are equivalent, and the first one is A inverse exists. The second statement, let me write this like this. The second statement is states that AX is equal to B has unique solution for any B, element in Rn. I think we know this one because the moment that A inverse exists, we can multiply both sides of the equation with A inverse, and we get a unique answer for A inverse times B. This is the second equivalent statement. The fourth equivalent statement is the following: AX is equal to 0 has only the trivial solution. So I think we know this one has only the trivial solution. The fourth statement is the following, so we can write it like this. The fourth statement, it states that reduced row echelon form of A, is equal to what? This is
identity matrix n times n.
That's correct. That's an identity matrix, which is n by n. That's true. Then the fifth statement, it is the following, which states that determinant of A, it is something. Determinant of A, it is different from 0. Then here we have a sixth statement, which states that the rank of A is equal to n, and the rank of A equal to n is also equal to the number of leading ones. Okay. So this is true, and then we can say also. So this is the sixth statement. The seventh statement is the following: columns of A, Ci of A, are basis for Rn. Okay, we can say this. We can also say the following: the columns of A are basis for Rn. We can also say that the rows of A are a basis for Rn. Okay, so either the rows or the columns, they can serve as a basis. This is the basis. The next discussion that we can continue. Wait a second. So this is the basis. Let's think about of any possible example here. Okay. So we can come up with a vector 1 minus 1, 2, another vector which is linearly independent to this. How can we construct a vector which is linearly independent to this? Let's multiply them by 2. We get here 2 minus 2, 4. Now, in order to make them linearly independent, we can, from 4, we make this 3. Then, let's make another vector. Let's add these two together. 1 plus 2 is 3, minus 3, 5. Now, these are linearly dependent. In order to remove this linearly dependence, let's make this from 5 to 4. Now, we just made up this matrix, and the question is, does the inverse really exist? And in order for us to read this carefully, we have this statement with this here, 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 and here, and here. So these are the statements which are to be equivalent. Now, what is the determinant here? This is 1 minus 8 plus 9 minus 2 times minus 4 plus 6. This is 2 plus 3 times minus 3 plus 4, 1. So this is equal to 1 minus 4 plus 3. Is it really 0? Can you check this? Minus 8 plus 9. Minus 2 times. I really try to make up a linearly independent. Wait a second. Okay. So it ended up being determinant 0. So we are so good at randomly producing these kind of matrices, but let's see. Is it correct? Is the determinant really 0? Can you check this?
Yes, the determinant is 0, and also we can say that the second row is minus 1 times the first row, so they are dependent, and it should definitely be 0.
Okay, so let's cause some damage. Okay, how do you tell me?
Now it's 6.
That's true. Actually, yeah, because I was trying to add these like this, but we have to also
yeah, we got the rows. Now it's 6.
Okay, so here the determinant of matrix A, this is equal to 6, which means that in this case, the A inverse exists, determinant is equal from 0, the
Rank is equal to 3.
Which one?
The rank.
Yes, the rank is equal to 3, but more essentially is that the columns of A, they all serve as a basis of R cubed, and the rows of A, they can also do the same. Now, with this discussion, we can start talking another definition, which is important, which is the coordinates, okay? So, regarding the coordinates, let's give the following, here we have coordinates. So now we know the basis, and let's assume that if S is a vector which is composed of V1, V2. Actually, let's move it this way. So now we know what basis is. We know that basis can be an infinite number of different combinations. And let's talk about the coordinates. And here we say that if S, which is composed of vectors V1, V2 Vn is a basis of vector space V, then any vector V, which is a member of the vector space V, can be expressed uniquely, which means that in only one possible linear combination as alpha I Vi. Sorry, this is not true. So we can express this uniquely, which means that alpha 1 V1 plus alpha n Vn, this is equal to V. Okay. Then alpha I are called the coordinates of V. The coordinates of this vector V with respect to basis S, with respect to basis S. And we denote this as, we call it like this. So we have this vector V according to basis S. This is equal to alpha 1, alpha 2, alpha n, and this is all equal to a vector which is called alpha. Okay? Now, this principle of, not the principle, well, yes, we can say it this way, the concept of coordinates is very useful and it is very much needed because we will need often in linear algebra to transform from one basis to another. So let's say we can have the same vector, but we want to project it onto different coordinate systems. And as an example, let's assume that we have a basis which is composed of 1, 0 and 0, 1, and this is the basis. This is the basis B, and let's assume that we have another basis S, which is composed of 1, 2 and 1 minus 1. So here we have two different bases. And we are sure that, what would you say? Can the B be a basis for R squared? What do you think?
It is a basis because it spans R squared, and because 1, 0 and the 0, 1 are linearly independent from each other.
Yes. What about this? Is this a basis?
Yes.
Yes, the two.
It is a basis.
That's true. Then we can always do the following. What is the determinant of this matrix? It is 1, different from 0, so it's a basis. What is the determinant here? It's minus 1, or no, it's minus 3. It is different from 0, so it is a basis. Okay, so we can also argue in this way. Now, let's try to identify. We have a vector V, which is equal to 2 minus 5. Now, we want to represent this vector as this vector in terms of these bases, okay? Which means the following: we want to have C1 times 1, 0 plus C2 times 0, 1. Okay. At the same time, we want to write here this is equal to C3 times 1, 2 plus C4 times 1 minus 1. Okay. So this is now the question is, what is C1 and C2?
C1 is equal to 2 and C2 is equal to minus 5.
That's true. This is minus 5. What about C3? What is C3?
Well, we should construct the system C3 plus C4 equal 2, and 2 C3 minus C4 equal to -5.
C3 is -7/3. Sorry, -1, not -7.
Before a moment, someone was saying C3 plus C4 is equal to 2, right?
Yeah, I said that C3 plus C4 is equal to 2, and 2 C3 minus C4 is equal to -5. And we can just solve the system. Okay, if we add them, we get 3 C3 equal to
-3.
-3. C3 is equal to -1.
Yes.
And then we get the C4 is equal to 3.
Okay, this is -1. And C4 is equal to 3, right? 3.
Yes.
Okay, now this problem, we can also write it like this. So this is, because this formulation, we know that this is C3 plus C4, right? So when we add this, if we look at this construct here, we already found the answer, okay? But just as what can lead us, what is C3 times 1? This is C3 plus C4. Then we have 2C3
-2.
minus C4, right? Well, I'm still here.
Okay.
I'm trying to write it like this, and it is clear that this one can be expanded like this, right? It's the same thing. So in principle, you are right. The problem is solved. We have the answer right here. But we also remember that we can solve this problem by writing it in this form, and this would be equal to 2 minus 5. And how do we solve this problem? You are specialist in doing this.
We use
Reduce row operation.
We do the augmented matrix, 2 minus 5, and we try to get the reduced row echelon form. We get the answer from here. You already did a good job here, but now the answer that we are looking for is the following. What is the vector v according to basis b? This is equal to 2 minus 5. Okay, because the projection of this vector on these coordinates, this is what it is. Then we can also ask the question v, what is the projection of v on basis s? What is it?
Once again, 2 minus 5.
No?
-1, 3.
Yes. It can be, right? Would you agree with this? So this is what the projection should be. Now, so in the vector 2 minus 5, two minus 5 is 1, 2, 1, 2, 3, 4, minus 5. So this is the vector 2, and we're looking for the vector 2 minus 5, which is this. Actually, before solving this problem, let me answer this. For a vector which is 3, 2, minus 3, what is the projection of this vector onto z-axis?
-3 is 0, 0, -3.
That's correct. Okay. Now I'm switching just for a moment away from this one, just also to pick up how fast we are with our intuition. So the projection of this vector onto z-axis is -3. So we define this one as the projection onto z-axis. It shouldn't be a problem for us to switch like this. What is the projection of this vector onto x-axis?
3.
But is this unique? Is the projection of this vector only -3 along the z-axis? Yes. In the definition that we wrote here, that I just erased, it was specified that if we have a basis, then the projection of any vector can be described in a unique way, which means that in a single way. So the coordinates, there is only one set of coordinates for each basis. If we are using the Cartesian coordinate system, the projection of these three onto the Cartesian coordinate system along the z-axis is always -3, which means it's unique. The projection along the y-axis is 2. So this is y-axis. So for each basis, we have only one set of coordinates or only one projection, and it is unquestionable that this is true. But these numbers might change if we project them in a different basis. Now, let's have a look here. This is the vector 2 minus 5, which is here, and this is equal to what? This is equal to, where is
The basis of V related to B on the right.
2 units along this direction, minus 5 times 0, 1. This is what we get. But now, what is this other basis? The other basis is 1, 2. Where is 1, 2? It's 1.
No, it was minus 1, 3
But now
on the right. Right.
the basis is 1, 2. Okay?
No, the basis is minus 1, 3. Look at the right. You have written there V with base B and we with base S.
Okay? But what is the basis? Why don't we have a look at this one?
Because we didn't have a look at that one for the first vector. We had to look to the right. Look at the right.
But I'm asking, what is the basis? We said that, so how do we read this one? This means that the coordinates...
Those are the alpha values, but the basis is the 1, 2, and 1 minus 1, I think.
That's true. That's what I'm trying to show. So this is the basis, okay? This is the projection or the coordinates of V according to the basis S. The coordinates is a different thing, so this is the coordinates. But now I'm asking about the basis. So this is one of the bases.
And why did we draw the basis of B there? The 2 minus 5 is the basis of B.
This is a little confusing, you are right, because in the standard basis, where we use the Cartesian coordinate system, the coordinates, they can be extracted easily because of reasons which are clear here, okay? But the basis is this, and so the basis, actually 1, 0, 0, 1 is going to be this. So this is 1, 0, is this vector, and this is 0, 1. Actually, this is the initial basis. The initial basis is 1, 0, 0, 1. This is how it looks like. What is the second basis? The second basis is 1, 2, which is a vector which is 1, 2. So it's this. And the other component is 1 minus 1. So we move this much, okay. So this is the basis B, okay? And this is the basis S. Okay, so these are the bases. Now, we are trying to determine the coordinates. Is it clear now that I try to do this? This is
Yes.
Yes.
Say it again.
Yeah, once again, the basis.
1, 2.
Yes.
Once again, I made the same mistake. Yes, this is here. So the projection here is both 1. Okay. Now this is better. I mean, the previous one was slightly wrong, but now, okay, this is, but here we did the good way. Then the other basis vector is this one, is this small vector right here. Now the question is, how did we get this 5 minus 2? Let's see the coordinates. C3, it multiplies it by minus 1. What is minus 1 of this vector? It's going to be this vector, right? So with this vector, which is filled in black, then we add 3 units of 1 minus 1, which means that we move 1, 2, and 3. So, or we can move 1, 2, 3. 1, 2, 3, so we get here. So this vector here is in fact 3 times this other vector. So we can confirm that we can get this vector 2 minus 5 by having minus 1 of this vector, which was here, plus 3 times of this, which is 1, 2, 3. So we can confirm that these coordinates, which are given here, they produce the same vector. Now I can ask you this question. So for a moment, we have here the vector 2, minus 5. This vector 2 minus 5, what is the projection of this vector onto 1 minus 1? So onto 1 minus 1, what is the projection of this vector?
7.
What was it?
7. 2 plus 5.
No.
The inner product, right?
No, it's not that. Oh, let me think. It's going to be equal to 3, yes. So, actually, it's going to be 3, but let me think for a moment. So, you said we do the inner product. You have a very strong argument there, but think about this one for, let me think. How do we find? You said 7, and the projection of a vector onto some other vector, it is in fact defined as follows. Or let me do it like this. So this is vector A, and this is vector B. What is the projection of A onto B? In fact, maybe I'm not 100% correct here, but for you that correctly mentioned that we said we do the inner product, in fact, we can do it like this. The projection of A onto B is equal to A inner product with the unit vector, which is along the B. And the unit vector along the B, so now this is a more correct way. This is equal to times B over the magnitude of B. So this is the proper definition of the projection of A onto B. Probably I can say it again.
We can see what.
Oh, sorry, that's okay.
Okay, thank you.
I missed that part, sorry. Now, maybe here, a better question is this. How many units of this vector would fall onto this? So we can see this. What is C4? This is what we're trying to ask actually. And how many units of this vector would be projected onto the direction along, what was the other vector? 1, 2, right? This is 1, 2. And what would be the answer here?
-1.
It will be -1.
-1.
Because we can see it from the answer that we provided. But I made a small mistake when I defined that one as a pure projection onto these, and the more, maybe it's better if I can ask you this: how many units of this along this axis? How many units of the we're going to have? This is going to be just 3, and here we get the -1. But as a reminder that you did to me, you can go back and the formal projection of any vector A onto some on the direction of some other vector B. This is how we would define it, okay, as it's shown on the part of the board. Okay, now this was we did the basis, the coordinates, and the next material that we want to go over is, in fact, we have to talk about the dimension. But for today, I think we are running out of time, and we will continue the discussion of the dimension and the basis of dimensions in. So the next topic that we are going to discuss is, which remains for the next session, is dimension in general. Then we have to talk about the column space of A the row space of A, of any matrix A, and the null space of A. This will be the next topic. But for today, do you have any question? Any more questions of what we covered?
No.
Professor, the difference between the range and the basis of a matrix, in this case, the range is the same as the basis?
What do you think about it? You are saying the range and the what?
And the basis of a matrix.
A matrix does not have a basis. The columns of a matrix can serve as a basis for the space. Okay.
Yes, but if we were to transform the vectors that we have taken as example in a matrix, then it would be the same as finding the range of the matrix. Is that right?
No, let me write them down because I get confused. So you are saying that the range of a matrix A, okay, and we are discussing also the possibility of the basis of what? So let's do this step by step, and maybe you answer this question better than me. So let's assume that we have a matrix which is 4 by 5, okay?
No, we can take, for example, let's take this the basis as 1, 2, and 1 minus 1 that we have taken as an example below.
That's good. We have here 1, 2, and 1 minus 1. Okay.
Then
So,
finding the range of that matrix is it will give us the same as the basis of S.
no, let me say this one. The range of A is R squared. What does this mean? We can describe any pair of numbers in R squared. This is the range. Okay? Pra kjo skanon të gjitha hapësirën dy-dimensionale në mënyrë perfekte, the range of A, it can cover all the space. It is not constrained into a line. Okay?
Okay, e kuptova.
It's
Do
good?
thjesht
Okay.
ishte u konfuzova. Po, kuptova.
So but for Shumiche, that's good that you caught this one. But then the basis that we are talking about, what we can consider here, because this is a 2 by 2 matrix, we can consider the basis. So what is the basis? One basis for R squared is this: 1, 1, 2 minus 1. This is a basis. Where did this come from? The rows of the matrix A, they can be the basis of the R squared, right? Because we had the theorem where we stated that if the determinant of this matrix is different from 1, which it is, then the rows are the basis for R squared, okay? Now, this was a basis. Another basis is this: 1, 2, 1 minus 1. Is it good? So this is another basis. Where did this come from? These are the rows, and these are the columns. I think you understood this one, but I'm just adding a little more. And similarly, we can also discuss the following. We can, if we have a matrix which is 4 by 5, the rows on this matrix, they can span, or their candidat për të skanuar, they can span what? R what?
R4, the maximum.
So the rows, this is a matrix which is 4 rows and 5 columns. So each row has 5 elements. So this is R5.
Yes.
Would you agree with this? Sometimes
Yes, because there will be 5 variables, so the space will be 5-dimensional.
Yes, or I can do it myself. I often get confused. So if you're talking about the rows, what would be a row here? 1 minus 1, 1 minus 1, 1. Right? 4 by 5. So this is a row which is composed of 5 numbers. So this means the row span R5. Okay. Now, also, if we have 4 columns, we say that the column will span the R4. Now, I just wanted to mention this one because in the case of 2 by 2 matrix, the column space and the row space, they have equal dimensions, which would be 2. In the case of, is it clear?
Yes, that's clear.
Okay. Your question started between whether these are the same or not, okay? Which are not, apparently. Any other question?
Professor, when we had the previous example where we had 2 vectors and we said that they're linearly dependent because the other is a multiple of the first vector, can we just say that the span of that vector is a line that goes through origin and that vector?
I believe yes. Yes. Well, yes. Let me write down what you just said. So I believe you said that if you have a vector which is 1 minus 3, and you said that we can have another vector which is linearly dependent on this one, right?
Yes.
Which can be 2 minus 6. And these two vectors, they are linearly dependent, and they constitute a matrix which can look like this. And the range of this matrix, it is simply, so the range of this matrix A is defined as the linear combination of the first column plus the linear combinations of the first column and the second. But since they are linearly dependent, we can simply state that this is any constant L times 1 minus 3. Now L is a real number, which means that L can even be 0. So the range of A, it does include the 0, which means also that it is a line. Yes, what you said is true. I tried to put into numbers what you said verbally.
Thank you.
You're welcome. Any other question? Okay. Any more? If this is all, we can